Hey, everyone. So we're starting the afternoon session now. I hope everybody had a nice lunch and was able to make it back, you know, energized and ready for the next couple talks. So yeah, I have the pleasure today of introducing Sandra Zilles. You know, this is one of those relationships, Sandra. You don't know this, but I've read many of your papers, and so this is almost like a fan, you know, a fan situation right now. So yeah, no, I think we're very lucky to have her speaking today. Unfortunately, she couldn't come in person, but Sandra's an expert in formal languages, CS theory, AI, and kind of how these all come together. And so I think today's talk is going to be very interesting, particularly in the context of trustworthy AI. So I'll stop talking and hand the floor over to Sandra. Thank you.
Thank you so much, Marcel, for that really kind and nice introduction. Thank you also to the Simons team for allowing me to speak remotely. I'm really sorry that I can't be there in person. I so badly wanted to next time. Okay. Last year it got canceled. My flight got canceled a day before I was supposed to fly out to Berkeley. Yeah, it doesn't seem to want to happen. Next time it will. Okay, so today I would like to tell you a little bit about a few years of research that I was involved in with a number of people on formal models of machine teaching without collusion. And this morning, Jerry already promised a lot of things that I would talk about. I'll try to fulfill his promises. I'm doing my best. When I prepared the slides, I wanted to say so much more, but I realized I won't have enough time. So I unfortunately have to cut a few things out of the talk, but I think I hope I'll be able to give you a nice little overview of what we mean by machine teaching without collusion and in which directions this could connect with things that you might be interested in. As you can see, here is a long list of collaborators. Highlighted here are the students without whom my slides would be pretty empty. So I just want to thank my students in particular for putting in so much effort and driving the research forward. And yeah, so let me just dive straight in. Imagine you're in the following situation. You have to somehow figure out how to automatically construct C++ programs that perform a specific task, some specification that you're given. The goal is maybe to find a small set of input-output examples that would allow for automatic synthesis of a correct and complete program that does the job. So in formal verification and in program synthesis, you have the ability to tailor algorithms to the selection mechanism for input-output examples, right? Because perhaps you have some idea of how that selection mechanism works. And if you have an idea of that, then you can tailor your synthesis algorithm to that notion. In machine learning, we are looking at in that sense, at the problem of tailoring learning algorithms to the properties of the source that provides the training data. And that is my view on machine teaching. And that's maybe one aspect of it that was also touched upon this morning in Jerry's talk, but that's one that I would like to emphasize a little bit more here. So if you have a machine teacher, that teacher has properties, and if the learning algorithm knows some of the properties of the teacher, that could be exploited. Here's another situation. Suppose your requirement is to design an agent that communicates effectively with other agents in some decentralized system. Maybe the agents do not all speak one another's language. How can we find a small set of examples that allow one agent to understand my agent's language? So communication in multi-agent systems might face the task of somehow tailoring agents to the anticipated properties of other agents. So these other agents are maybe different than my agents, but maybe I have some idea of what they would behave like. In machine learning, again, this corresponds to the same I said before, tailoring the learning algorithm to anticipated properties of the data source. And that's my idea of machine teaching. In a nutshell, if you learn from randomly chosen data, you need more data than if you learn from carefully chosen data. And what I'm saying is you can go one step further. If you not only learn from carefully chosen data, but tailor your algorithm to the properties with which those data were carefully chosen, you can learn yet even faster. That's basically my core view of machine teaching. So why should you care? I'm basically want to tell you, if you like machine learning, if you like formal methods, or if you like multi-agent systems, then you might like machine teaching. If you don't feel addressed by that yet, if you like formal languages or hypergraphs or geometric objects, graphs, matchings, Boolean functions, anything that has nice structure, or if you're interested in computational complexity, all of these things are studied in the context of machine teaching. So you would find something there that would interest you, I bet. And of course, I don't have time to go over all of these things and reach you if you are maybe interested in Boolean functions. Maybe you won't get very much out of this particular talk, but you should talk to me and I can give you pointers. All of these aspects and many more are studied in the context of machine teaching somewhere. So here's the formal setting that I would like to use during this talk. Suppose you're given a set X, which we call the instance space. Now a concept could be something that we want to learn. A concept C is just a subset of X. So here in this picture, X is the Euclidean space, and a concept here is given by this rectangle. It's just a subset of X. A concept class is a set of such concepts. So here I could have the class of all orthogonal rectangles, for example. A labeled example is a pair that consists of an instance X in the instance space. So here a point in the plane, and a label L that indicates whether or not that point X belongs to the concept C. So in this case here, I've labeled the positive examples red and the negative examples blue. Negative examples have the label 0, positive examples the label 1. And that's the whole kind of setup that we need to formulate various models of teaching and learning. Here's a very simple example, one that Jerry also used this morning. Suppose you want to learn an unknown threshold on a line, and suppose you've got just n data points numbered from 1 through n, so discrete data points. Your threshold is some point on that line, and everything below the threshold is 0, everything above is 1. So suppose first that the labeled examples are chosen randomly, then of course you cannot ever be guaranteed to determine the threshold exactly. So somebody gives you labeled examples, you being the learner, and you see a few positive ones, a few negative ones, and you'll put your threshold somewhere in between the positive and the negative ones. You might be a little bit off, right? You can't be guaranteed to find it exactly. If you want to have a high probability to get at most a fraction epsilon of incorrect predictions with where you place your threshold, then that would require on the order of 1 over epsilon many examples. That is a well-known basic fact. There's nothing really you can do about it. Now, however, suppose you are a somewhat smarter learner and you say, okay, don't give me random examples. I will tell you the examples for which I want labels. And I will first pick this point here. Please give me the label. Okay, now you will see the label is negative. You know, oh, the threshold must be on the other side. I'm doing binary search and I'll pick my next example here, and you'll find out it's positive. Now you know the threshold is in between those values. The third example you ask, is in the middle between those two until eventually you will say, okay, I've seen enough. I will now make a prediction. I'll predict the threshold is right here or right there, whatever. So if you do this kind of binary search, you can actually find the unknown threshold exactly with log n many examples. We know that, right? So that is nice. But if you have a benevolent teacher, you could, of course, learn this threshold with only 2 examples. The teacher could tell you, okay, this point here is labeled positive, and this point there is labeled negative. Okay, well, because I have a discrete setting here, there's nothing in between. You know exactly where the threshold is after just 2 examples. If you are a consistent learner, something that Jerry called version space learner this morning, so that it just guesses a concept that agrees with the labels on the examples it has seen. Okay, so far so good. It looks like if the teacher is really nice, you can save a lot of effort here. Now, one core question, and that's also something Jerry hinted at this morning and promised that it would be addressed in this talk. I'm glad I had prepared slides to that effect. Does the same combinatorial structure that determines how difficult it is to learn a concept class from random example, does that also tell us something about how difficult it is to learn a concept class from a benevolent teacher? Why do I ask this question? Because learning from random examples, that is very well studied, has been studied for decades, and there is lots of results on this, and we understand this notion fairly well. Not so much what makes sense and can be done with a benevolent teacher. So in my world, the way we assess the sample complexity, so the number of examples you would need in the worst case to learn a target concept from a concept class, that is something that we assess in terms of combinatorial parameters. And these combinatorial parameters, we have some for learning from random examples, and we have some for learning from teachers. And one of the things I'm interested in is comparing those so that I can answer this very core question here. Okay, so we should know, first of all, what are these core parameters? In learning from random examples, it's the so-called VC dimension. Again, something Jerry mentioned this morning. So I will first tell you what the VC dimension is, and then I will tell you what the teaching dimension is and what I mean by collusion freeness. So in essence, we will be talking about relating the VC dimension to the teaching dimension or other notions of teaching complexity. In particular, I will talk about 2 variations of the teaching dimension model called preference-based teaching dimension and non-clashing teaching dimension, PBTD and NCTD. And there's some interesting open questions there that I would like to introduce you to. And finally, I would like to revisit the notion of collusion freeness that we have underlying under all of these models, TD, PBDD, NCTD. They all follow this notion of collusion freeness. And I'm arguing maybe it's not the one and only notion of collusion freeness we should be looking at. Maybe we should be more open-minded about collusion freeness, and that leads to another teaching model called STD-Min. So that's roughly the outline for the next 40 minutes or so. The VC dimension. Many of you will already know what it is, so I'll try to go over this fairly quickly. The VC dimension of a concept class is just the size of the largest subset of the instance space, such that the concept class realizes all the bit patterns over that set. So if I have a set of size 5, a subset of size 5, then there are 2 to the power of 5, 32 many bit patterns that I could realize over this. And if they all show up in the concept class for this subset, then this set is, we say, shattered. And if I can do that with a set of size 5, but not a set of size 6, then the VC dimension is 5. Here's an example, the axis-aligned rectangles from before. I'm claiming the VC dimension is 4. So to prove that it's 4, I have to show there is a set of size 4, set X of size 4 in the Euclidean plane, such that all the 16 different bit patterns are realized by rectangles. What does that mean? So here I've picked 4 points. I want to show that this is the bit pattern all 0, meaning none of the points are contained in the concept. There is a rectangle that contains none of them. This is a bit pattern where 3 points are 0 and 1 is 1. Obviously, I can do that for all of the points. This is one where 2 points are 1 and 2 are 0. Also for these 2 points, I can do that. So you can imagine I can realize all of the bit patterns, all the sets of size 3, and also finally a rectangle that contains all of these points. So all these are realized. So the VC dimension must be at least 4. Why is it not more than 4? So here, it's very easy to argue, no matter how I choose 5 points in the plane, not just these 5 here, but any 5 points, there will always be 1 point that is contained in the smallest rectangle containing the other 4. So if I now want to realize the bit pattern where these 4 points are inside a rectangle and that 5th point is not, I can't, right? So this is why the VC dimension is 4, not 5 or higher. And why are we so thrilled by the VC dimension? Because we know that the sample complexity of PAC learning of a concept class is linear in the VC dimension. So that we can express this basically as a function linear in the VC dimension. One side of the bound is very old and the other one is actually still fairly recent to that the gap between upper and lower bounds was closed. So that's why we love the VC dimension. One of the reasons we love it. Now, the question is, how does learning from random examples relate to learning from a benevolent teacher? Meaning, how does the VC dimension relate to the number of examples I need in a teaching model? Okay, so here is what it all began with, the teaching dimension. Jerry has already introduced it this morning, but that's been a few hours and you've seen lots of other stuff, so you may have forgotten. A reminder, what does it mean to teach a concept? So my world of possible concepts is this concept class C, and there is one particular target concept in there that the teacher wants to teach to the learner. To teach this concept, the teacher provides a teaching set of labeled examples. So the teacher is a mapping that I apply to the concept C, and out comes a set of labeled examples. And these labeled examples should be consistent with C, so they should agree with C, right? I don't want to put the wrong labels on there. And at the same time, it should disagree with all of the concepts in the concept class C that are different from C. Why? If the teaching set has this property, then that means the target concept C is the only one in the entire class that agrees with these labels in this teaching set T of C, and therefore I have uniquely identified C. Okay, the teaching dimension parameter, how is that now calculated? If I look at a specific concept C in the class C, then the teaching dimension for that concept C is just the size of the smallest such teaching set. Jerry said this morning, there are many options for teaching sets, and some could be larger and some could be smaller. There could be many smallest ones. The size of any smallest ones is the teaching dimension of that concept. And the teaching dimension of the class is now just the worst case teaching dimension taken over all concepts in the class. Or if the class is infinite, I'll just take the supremum. So this goes way back to Goldman and Kearns, but also Shinohara, Miyano studied this independently. So that's the teaching dimension. If you have any questions, shout out loud. Okay.
If you have the same example as before, the orthogonal rectangles,
Yeah.
what is the teaching dimension in that case?
So in that case, if it's a discrete space, then you could make do with 4 examples. You would pick the 2 opposite corners and then something outside that to tell you.
But it has to be discrete, right? Otherwise, it's
Yeah.
infinite. Yes.
Yeah, but otherwise it's infinite, exactly. And
Yeah.
I have an example to a similar effect coming up right away.
Okay,
Here
thank
it is. Okay, so teaching dimension of circles in the R2 with positive radius. So if we have a circle, just a line, not a filled circle, just the circle itself. If I put 3 vertices of a non-degenerate triangle, then the circumcircle of this triangle will be uniquely described by these 3 positive examples, right? If I take these 3 positive examples, it can be only this circle, none other. If I have only 2 examples, whether they're both positive, both negative, or one of each kind, you cannot possibly teach a circle. And therefore, the teaching dimension of circles with positive radius, strictly positive radius, is 3. Okay. Now, however, if I look at the balls containing the interior as well, again, with positive radius, then these 3 positive examples are not enough because now there could be a larger ball containing them. So I want to put negative examples to prevent a larger ball. But now again, if I don't make things discrete, I can't put the negative examples infinitesimally close. And so the teaching dimension will be infinite. I can always squeeze an extra ball between the positive and the negative ones. So that's the teaching dimension. And as Jerry said this morning, the VC dimension and the teaching dimension are actually not related at all, unfortunately. In particular, as he said, there are examples where the teaching dimension is arbitrarily higher than the VC dimension and vice versa. So does that mean teaching and learning from random examples has nothing to do with each other? Well, if teaching dimension is the only model you're looking at, then yes. But I've studied the question, can we cast teaching in a different way so that its complexity is bounded from above, either by the VC dimension itself or, say, a function linear in the VC dimension? In particular, the idea is here that the teacher selects helpful examples and the learner uses knowledge of the selection process. Like I said in the very beginning in my hypothetical situation, somehow we want to use here, the learner of the teaching dimension model only has to be consistent. It doesn't need to know how the teacher chose these examples. It just is consistent, aversion-space learner. That's not a particularly smart thing. It doesn't use any extra knowledge. How about designing a teacher-learner pair where the learner uses knowledge of the selection process? This has led to a series of studies of smarter teaching learning protocols, and a couple of them I will introduce next. But there is this one other word in the title of my talk, and that's a collusion-free. So we want to not make the teacher-learner pair arbitrarily powerful and trivialize learning. We want to say, okay, you guys have to follow some rules. You cannot collude. What would be an example of collusion? Here you could, for example, say, oh, I want to teach these balls. I could just teach a ball that has center xy and radius r with 2 labeled examples, namely the center and the North Pole. This would be the center and the North Pole, right? Easy. Okay. And if the teacher chooses examples this way and the learner knows that the teacher chooses examples this way, then you can decode it's all fine. You can teach with 2 examples. All right. Now consider this, these 3 balls here, and now consider this additional point. Here's an additional positive example for the orange ball. It's neither the North Pole nor the radius, just some other positive example. Now, if the teacher gave you these 3 points, then you would say, okay, why are you giving me these 3 points? Are you maybe talking about the orange ball? Or are you talking about this big red ball? Because that's the ball for which this point is the center and this is the North Pole. So now you can't disambiguate. And this would be a problem if you want to have a collusion-free teacher. What does collusion-free teaching mean? This is a model that goes back, again, decades to Goldman and Matthias. So a successful teacher-learner pair, as we already discussed and just haven't written down formally, consists of a teacher that maps every concept to a teaching set of labeled examples that are labeled according to the concept C. And the learner is a mapping that takes in the set, T of C, and has to decode into a concept in the class, and it better decode T of C back into C, else it wouldn't be successful. So this pair of teacher and learner, TL, is collusion-free for the concept class C if the following property holds. So the property just says, if I take the teaching set for C, and now I add additional points to it. So I add more points that are labeled consistently with C, like on the previous slide, I added 1 more point consistent with the orange ball. Still, the learner has to say C. You give more information consistent with C, it still says, yeah, C, I know already, you told me it's C. Yes, give me more information consistent with C. Yes, it's still C. The learner cannot suddenly say, oh, now that you give me more consistent information, I'm going to change my mind. So this is the idea of collusion freeness. And if you actually require teacher and learner to be collusion free in that sense, you can get rid of a whole lot of nonsense, like some things that Jerry pointed at this morning, some behavior that you don't want between teacher and learner. And it also fits well with Jerry's notion of attack through data. So this kind of collusion-free pair would be resilient to a third-party attack that just adds consistent examples to the teaching set, right? So in that sense, it also fits to something else that Jerry pointed at. So it looks like a sensible model, and it's been accepted as the one true sensible notion of collusion freeness for decades. Another model that we looked at is the so-called no clash teaching dimension. Why? We started off with that very notion of collusion freeness and said, okay, if that's all that I want from the teacher and the learner, to be collusion free and successful, of course, then what's the best I could do? What is the best possible notion of teaching dimension I could get? And what we proved a few years ago was that, and it's actually very easy to prove, it's just a 5-line proof or something. A teacher for a concept class can be paired with a successful learner so that the two of them are collusion free if and only if a very simple property is fulfilled for that teacher. Namely, if there are 2 different concepts, C1 and C2, then you have to have C1 inconsistent with the teaching set for C2 or C2 inconsistent with the teaching set for C1. So one of them is, it's okay if C1 is consistent with the teaching set for C2, so long as it doesn't hold the other direction as well. So that's the property that we call non-clashing property. The teacher with this property is not clashing. The name is borrowed from sample compression literature, where the same property is used in sample compression and called non-clashing compression. And the same property is also known under the name of... Yeah.
Sorry, to come back a bit to the previous slide, because one condition is that the learner exactly guesses what is the concept class. But is there a
Right.
notion of approximately learning the concept class as well?
Yes, that exists as well. Absolutely. I'm not covering it in this talk, and it's
Okay.
not as well studied, but it's a very good question. Thank you. That exists. There are some studies on it, and it's more also along the line of what Jerry would be more interested in, because it's more towards the practical settings. This is very abstract. I admit that. But yeah, here we're looking at the exact case.
Thank you.
So if you have heard of characteristic sets in grammatical inference, that's also actually in essence the same as, or at least they fulfill the same non-clashing property. So it's a property that shows up in various contexts, interestingly. So because collusion freeness implies a non-clashing teacher, this means that non-clashing teaching is the absolute, you can't do better than what you can do with non-clashing teaching when you want to be collusion free. So this is why we defined the no clash teaching dimension. So if you have a non-clashing teacher for the concept class, what is the order of that teacher? The order is just its worst case teaching set size that it ever produces on all the concepts in C. So it says, okay, this concept has a teaching set of size 5, this one 4, 3, this one 4, and the other one 5. If 5 is the worst it ever says, then that's the order. The non-clash teaching dimension of the concept class is now the best possible, smallest possible order of a non-clashing teacher for that concept class. And because of this theorem on the previous slide that says you have to be non-clashing if you want to be collusion free, the NCTD is identical to the optimal worst case complexity of collusion free teaching. So you can't get better than NCTD. Okay. Here's a very simple example. I won't go through it. If X is finite, my instance space, and I take the power set, so all the concepts over X, then the teaching dimension would be the size of X, but the non-clashing teaching dimension happens to be half that size. I won't go through the details. It's just a little example. Another notion of teaching that's important in the context of this talk is preference-based teaching. So we've just heard that non-clashing teaching is the best possible collusion-free teaching model. Preference-based teaching is also collusion-free, but satisfies a stronger sense of collusion-freeness, as we will see shortly. So what's preference-based teaching? In preference-based teaching, a teacher and learner first agree on a preference relation. So here is some knowledge that they share, right? A preference relation over all the concepts. And this preference relation induces a partial order over the concept class. Now, that means there's no cycles, okay? To teach a concept, we've seen before in the definition of teaching dimension, TD, we said to teach a concept means to provide a set of labeled examples that agree with the concept, but disagree with all of the other concepts in the class. In preference-based teaching, now we exploit the knowledge of that preference relation. In which way? We say, oh, this teaching set has to disagree with all the other concepts that are no less preferred than C. Okay, the ones that are less preferred than C, I don't care. They can be consistent with this teaching set. I would never guess them as the learner because I have a preference. I prefer C over them. So if you give me a teaching set for C that's also consistent with something less preferred, I'm still going to say C. Okay. So this is where that knowledge, that agreement on this preference relation kicks in. And that what that means is you can now reduce the teaching set size from TD because you don't have to worry about concepts that are less preferred. So if we fix the preference relation R and the concept C, then PBTD is the size of the smallest such set that you can get. And if we now don't fix C anymore, just look at the whole concept class. And again, we look at the worst case PBTD taken over all the concepts. And then PBTD of C is now the smallest possible PBTD if I'm allowed to pick the best possible preference relation. So choose your preference relation smartly, and then this is what you get, your PBTD value. Now, why do I bring this up? Because it's a nice example in this balls case. So we get back to the filled balls with positive radius in the Euclidean space. Recall the teaching dimension was infinite, but now if we have a very simple preference relation, namely we prefer circles with smaller radius or balls with smaller radius over those with larger radius, then we can show that the preference-based teaching dimension is actually at most 2. Because if I take these two red examples here, the orange ball is consistent with it. The green ball is also consistent with it, but the orange ball would be preferred over the green ball because it has a smaller radius. So I just have to pick two diametrically opposed points to teach a ball. And this is a very intuitive way of teaching as well. So in this example, it shows the power of a very simple preference relation to reduce the teaching dimension from infinity to 2. So what does preference-based teaching have to do with collusion freeness? So for one thing, I'm not going to go into the details. It's still collusion free because preference-based teachers have the non-clashing property. That's not hard to show. But they also, if we focus on finite concept classes, satisfy a nice, even stronger property. Preference-based teaching is basically equivalent to strongly collusion-free teaching. And strongly collusion-free here means collusion-free with a teacher that has the property, if I pick any other teacher for the concept class, then this teacher must not have the same range. Okay, so you cannot use the same teaching sets, but just assign them differently to other concepts. So basically swap the teaching sets around. That is also a natural property, but it's strictly stronger than the original collusion freeness. Okay, so NCTD therefore is less than or equal to PBTD because PBTD satisfies the collusion freeness requirement and NCTD is the best possible satisfying the collusion freeness requirement. We don't know yet how large the difference between the two can be. The largest observed gap is we have a family of concept classes where NCTD is a quarter of PBTD. So we know that for any value of k, we can have a concept class of NCTD at most k, whereas PBTD is 4 times k. And for those of you who like orthogonal matrices or signal processing, coding theory, cryptography, you may have heard of Hadamard matrices or Walsh functions, same concept. These are exactly, these matrices here with this pretty structure. These are the ones that we used as concept classes to show this theorem. So there is a connection to other fields here as well. Again, I said on the first slide or second, third, whatever, if you like theory of matching, you might like teaching. Yes. So you can look at teaching or teachers as a matching between concepts of the concept class and certain sample sets of size k. in the TD setting. So here I'm connecting a concept with its teaching set, and I'm drawing edges whenever a concept is consistent with one of those sample sets. Now, obviously, in the TD setting, no two concepts can be consistent with one teaching set. So that's why it looks so simple, this matching. In the PBDT setting, a concept, a teaching set chosen can be consistent with multiple concepts. In this case, this is consistent with 3 concepts, but that doesn't matter. It's okay, but we can characterize a PBDT teacher as a unique perfect matching. So you have to have a unique perfect matching in order for PBDT to work. And for NCTD, it can be even wilder. You don't need a unique perfect matching. What you can have also is, here, for example, this teaching set for this concept is consistent also with that concept, but you cannot have at the same time this going the other way. So you cannot have a 4 cycle. This is characterized as a perfect matching without a 4 cycle. It's basically an NCTD teacher. Okay, so and I forgot to say this matching theory is really nice because it helped us prove things about the computational complexity of determining NCTD, which is NP complete, and PBTD, which is NP. So you just need properties of those constrained matchings, which is a really nice topic in itself. Constraint matchings, there's lots of stuff in the literature. It's a really, really interesting topic. Oh, I shouldn't talk too much about it. I'm running out of time. Okay, so people have tried, as I said before, to relate those teaching dimension notions to VC dimension. And the most celebrated result probably we have in this context is now already 8 years old. It was shown that the PBTD is upper bounded by a function quadratic in the VC dimension. We do not know whether it is also linear in the VC dimension. We know it can be larger than VC dimension. It can exceed VC dimension by a factor of 5 over 3, but it might be still upper bounded by a linear function. We don't know. We also don't know whether NCTD is upper bounded by VC dimension or a function linear in the VC dimension or by VC dimension itself. There is still the possibility that actually the NCTD of every concept class is upper bounded by its VC dimension, and we just can't confirm or otherwise. A related piece of work, co-authored by Jerry, by the way, talks about sequential teaching, where you don't teach with a set of examples, but a sequence, and then you can encode information in that sequence. That has been published a few years ago, a sequential teaching model that really has a teaching complexity upper bounded by VC dimension, but we don't know whether it's possible in batch teaching if we want to be collusion free. Okay, so in essence, NCTD is our only hope to find a collusion-free model upper bounded by VCD, because we know TD, PBDD, NCTD, they're in decreasing order. We know NCTD must be upper bounded by a function of quadratic in the VC dimension because PBDD is. We know no concept class so far for which NCTD is actually larger than VCD. We haven't found a single one, but we haven't been able to prove that none exists. But a fact is that if there is any complexity parameter of collusion-free teaching that is upper bounded by the VC dimension or a function linear thereof, it has to be NCTD. It has to be one of them because NCTD is the best possible you can do in terms of collusion-free, right? So there's no way around it. That's why it's our best hope to find something. But, I highlighted this word here, collusion-free. What if we rethink that? What if we don't stick with this notion of collusion-freeness? And I want to give an example that might motivate this. Have you been in a situation like this? Somebody gives you a math assignment prove statement S under the premises A, B, and C. And now you go and write a nice proof, and it uses the premises A and B, but not C. Now you think, oh, I made a mistake because the teacher said use A, B, and C. I must use them all. If I can do it with less information, I'm making a mistake. This is you assuming that all the information you were given is actually important. What if the learner assumes that the examples chosen by the teacher are all important for the target concept? This has been studied before a long time ago in a model called subset teaching dimension, where we assume the teacher and learner both know all the minimal teaching sets, and the learner can now exclude, see in the teaching set, it can exclude a concept, of course, if it's inconsistent. Yes, I can exclude it. But you could also exclude it if you think the examples given are important. If no minimal teaching set for this concept would contain all these examples, well, then these examples, even if they're consistent, they're not important because they're not in a teaching set for this guy. So I can exclude this guy. In the interest of time, I will skip this example here, but this very notion helps you reduce the teaching set size, and you end up with something that's called subset teaching dimension, which is really nice and incorporates this idea of importance of examples, but it ends up not being collusion free. And of course it can't be, because why? If you assume all the examples are important, and now comes a third party and throws in extra examples, and you assume they're important, but they aren't, it can throw you off, right? But still, that notion of importance might be of relevance for many settings in machine learning. So if we want to incorporate that, we have to drop Goldman-Mathias collusion freeness. Instead, a property that this STD model fulfills is a weaker property, is an anti-chain property. So if I have two different concepts, then the teaching set of one should not be a subset of the teaching set of another. We can also add other interesting properties that we think we might want to postulate. So what I want to get at here is, instead of having one notion of collusion freeness, why not have something like 5, 6, 7, 8 sort of postulates? And you say, oh, in my current practical setting, I would need postulates 1 through 5 and postulate 8, but postulates 6 and 7 are not important for me. Then you can drop those. I would like to get at something like a list of interesting properties for teaching, and then try and see what you can do if you require a number of them. So is STD now the answer to our problems? No, because we already knew 15 years ago, STD is not upper bounded by a function linear in the VC dimension. But what we published fairly recently is a notion that's a variation on STD, and I'm not going into the details because I don't have time. It's called STD min. It's based on exactly the same idea as STD. We just tweaked a little thing in the definition, and we ended up with a model that satisfies the anti-chain property that I just introduced, and these other two properties, these postulates that I didn't even bother introducing. It does not satisfy collusion freeness, or strong collusion freeness for that matter, but it actually is provably upper bounded by the VC dimension. So it's the first batch notion of teaching that we know where this actually works, and this required dropping the collusion freeness condition because this big question mark here remains. Okay, sorry to take you so long. This is just a side remark. I'm not going into the details. I threw this in for the combinatorialists who really like this kind of stuff. And in this paper on STD-min, we also proved something about the smallest possible order of anti-chain teachers. We found some really interesting, all very close by upper lower bounds, showing that you can't do better than linear for teaching the power set, linear in the number of instances in the set. I'm happy to answer questions about that if somebody is interested, or just send me an email, please. So to conclude, I've introduced the PBTD as a notion of strong collusion freeness, the NCTD corresponding to collusion freeness, and the STD-min as the first batch teaching notion for which we could prove the sample complexity to be upper bounded by VC dimension. I would like to make a case for replacing collusion freeness by something like postulates, a set of postulates on reasonable teaching learning properties. And these happen to be satisfied by STD-min. Interestingly, to perhaps some of you who know about sample compression, our proof that STD-min is upper bounded by VCD uses techniques from sample compression. So there might be some parallels there. We had some interesting observations on relationships to bipartite matching, an anti-chain property. So those things might be of interest. But we have some core open questions, namely in particular the relationship between NCTD and VCD and PBTD. And VCD is not fully clarified yet. And also, I'm of course interested in what natural postulates can or cannot be fulfilled by any kind of notion X teaching dimension that is upper bounded by VC dimension. Sorry to take so much of your time. Please let me know if you have any questions. Thank you very much.
Great. Thank you so much, Sandra. We should have time for maybe 1 or 2 questions, and then we can start the break. So if there's any questions, yes.
Hi, Sandra. Thanks for a very interesting talk. I have a question on one of the examples that you gave about PBTD. So the one with the balls. So my preference relation is smaller balls, right?
Yes.
So if I give you an example in the middle of the diameter or somewhere along the diameter, wouldn't you return the smallest ball?
Yeah, so my teaching set is now going to be 2 positive examples that are diametrically opposed on the boundary of the ball. So if I want to teach the orange ball, I can pick any 2 points like these 2, or I could pick the North Pole and the South Pole, right? Any 2 points that are diametrically
You don't
opposed.
have to be bothered by additional points. That's the idea of this.
Yes,
okay,
exactly. Then if somebody throws in additional points, it won't hurt you.
Right, thank you.
Questions? I have actually one question myself. So my cartoon of preference-based teaching dimension is very much in the sense of like priors, that I have like I have a prior that the size is smaller or something like this. But what always falls apart when I want to extend this to more like Bayesian-based teaching is if I want to now include the likelihood, and so that I can model the posterior, and so teaching against these kind of systems. And so I'm curious if you see this relaxation of collusion freeness kind of enabling these forms of teaching models where I can properly include like a full posterior as part of the preference relation.
I guess that, that's a very good question. I guess that might be worth looking at. I believe that perhaps, do you know Jan Arne Telle? I think he attempted something in that direction. I have to check it. It should be published somewhere. I can send you that paper if I find it. But yes, and it's something that I have written in like 1 or 2 of my grant proposals that I want to do this at some point. So if this, maybe we should talk. Because I always stick so far with this very exact and perfect world, but it obviously makes sense to go in the direction that you mentioned. I haven't done it myself, but I think there is something for preference-based teaching out there.
Thank you. If there's no one else, thank you once again, Sandra.
Thank you, and sorry that I can't be there. Have fun, everyone. Party up for me as well.
Will do. So we'll start the next session. I think it's scheduled for 3:15. We can fudge that a little bit, give people a couple more minutes, but let's plan to meet back here at like 3:17-ish. All right. Yeah, of course.
Yeah, otherwise, here yet. Hey, Sandra.
Hi.
Can you see us? Oh, yeah. Thank